Welcome. Thanks, everybody, for coming out to Serverless Palooza. I wore this hat in solidarity with all the cowboys. It was the closest thing I had. So I'm here to tell you about, I'm an engineer, by the way. I'm here to tell you about Step Functions. It's a new AWS service that Werner introduced to the world this morning. So I'm going to claim in advance that this is a pretty simple product, and here's some objective evidence. So when I first sat down to write this speech, I took a lot of trouble to pare it down to the essentials, the bare things, the bare few things you need to know to decide whether you need this thing and how to use it, and that came in at 27 minutes. So I kept putting more stuff and more stuff and more stuff in, and I'm still maybe a little short of the full hour. So it's quite possible I'll use all the time if I go slow, and there won't be any for questions. If that's the case, I promise to go out there and stand in the hallway and talk about step functions until either you get bored or fall over. So let's plan on doing that. OK, any other introductory remarks? No, let's dive in. Let's look at the issues that step functions exist to solve. Now, let me see if this thing works. Oh, yeah, I should say that I saw on the program this was listed as a 200-level session, but it's not. This is a 300-level session, and there will be code. I hope that's OK. OK, sounds like it's OK. OK, so let's start here. There you go. There's a Lambda function, a stateless function living in the cloud. Isn't that a great thing? So I think we all got our minds expanded in 2014 when they announced that. And what else would you want? I'm done. You might want a little more than that. And I think the core idea of a stateless function in the cloud driven by events remains a very strong idea, and a number of people in this room suggests a few of you agree with me. But in real world, there aren't that many apps that only have one function, one entry point, one module, one component. So I think it's going to be more typical to see multiple functions in the cloud when we're trying to solve a real hard real-world problem. And in fact, more than just a few. A lot of functions in the cloud. You'll notice the arrows connecting them are different in color because there's more than one way for functions to interact with each other. Now, these are going to be real-world applications, and real-world applications have data. And if you have data, you probably have a database. And I've noticed that with cloud-native applications, there is very, very high usage of queuing and messaging technology. That gold thing is the icon for SQS, which is another thing I happen to work on. But there's lots of other messaging technology as well. And now I'm going to say something that may be in poor taste. Now, I realize that this is the serverless track, but they're still servers. The world still does have servers. And I think those of us living in the serverless future should be tolerant of the fact that the world has servers and deal with them. And it's worse than that, because this is a cloud conference, but sometimes those servers aren't in the cloud. They're just out there in a data center somewhere, and so probably at some point you're going to have to talk to them. So I'm going to claim that I have now built up on the screen here a picture of the real internals of a modern serverless application with the kinds of things you might find in it. OK, so let's subtract all the parts and just leave the arrows. They're different colors, as I said. And that's really the essence of what we're going to talk about here today, is how we actually, what those arrows are, how we actually coordinate and communicate with each other. So before we dive into the how of what we're going to do, let's talk about what people want to do. Now, you may have seen one or two of these slides in Werner's keynote this morning. He stole them from me, but that's OK. So I'm not going to talk about these right now because we're going to give each of these subjects a little love as we work our way through the presentation. But I think most people are going to say, when they see that. I mean, most people have wanted to run functions in sequence or in parallel or catch errors or run things for hours or route things to a function based on what's going on. None of these are terribly controversial subjects. And speaking of Werner, I want to give a nod to another subject he invested some time in, the 12-factor app idea. For those of you who have not read this essay, please do. I'm not dogmatic, and I don't insist that our junior engineers actually chant these like mantras, but I do care a lot about the questions the 12-factor app asks, and I try and ensure that people have at least thought about them. And I want to focus in on step 6 and read out the last paragraph there, which says, In well-architected application, state should be stored in a stateful backing service. That's what this is. OK, so I think we've agreed that it's a good idea to deploy and coordinate multiple functions in order to get our job done. And we know that because people are doing it right now. And let's talk for a couple of minutes about how they go about doing it. So probably the most obvious way to link Lambda functions together is to link them together into one great big binary and call from one to the other using good old-fashioned method dispatch. And I'm not going to say this is a terrible idea. I mean, if you look at the Zappa project, it implements more or less all of the Django framework, or actually any WSGI-based Python app, as a Lambda function. And that's fine. It's a really cool project, and I'm a fan. But I think we can do better. I actually am warmer to the idea of multiple independent Lambda functions in the cloud, each of them doing one thing well and dispatching to each other. I think we get better modularity, more of a microservices approach. So I'm not really crazy about this idea in the cases where you can avoid it. Being independent smells more like the future. Well, I guess the next thing you could think about for coordination would be using the good old-fashioned Lambda API, because from one Lambda function, you can obviously call another Lambda function and chain them together that way. Now, the question arises, am I going to make a synchronous or an asynchronous call to the other Lambda function? And I'm going to claim that if I make a synchronous call, I might as well just have linked them together at that point, because the first is waiting for the seconds, waiting for the thirds, waiting for the fourth, and so on. And I think that if you were going to do this, you'd really want to use the asynchronous call. That's more in the spirit of serverless anyhow. You have a function, it does something, it exits, and passes the workload on. And that's OK. People are doing that and getting OK results. But error handling and retries and things like that start to get tricky. When you call a Lambda function asynchronously, it can be quite tricky to figure out, did it run? Did it succeed? Did it fail? Now, people are doing this, but they're having to build a bunch of scaffolding and infrastructure to make it work, and it just seems like it's more work than it ought to be. Another approach that we're seeing a lot of, maybe this is the most popular approach, I think, that's being used right now, which is to use a database to stash your state as you move through multiple functions to deal with an app. Once again, I don't want to diss this because people are doing it and they're getting good results. And it's not terrible. But there's two problems with this. One is that you have to write the code to do it, which is kind of boring, non-productive, non-very interesting code. There's a deeper problem I think that we should worry about, which is the impedance mismatch. One of the great things about serverless and Lambda is that you get this great scaling behavior. If I have a throughput of so much and I suddenly need to do 10 times that much or 100 times that much, well, Lambda can do that. It just runs more functions. And I have discovered that with databases, when they're running at this speed and you suddenly ask them to run at 10 times that speed or more, well, they don't. It's just the way databases are. So I think you're going to have an impedance mismatch there that could lead to a not happy ending. The final way that I see people integrating functions together these days is with queues. Once again, that's the SQS icon. I actually have a lot of time for this approach. I think this is a good cloud-native, serverless tasting approach. And I've seen people get good results with it, and once again, there's nothing terrible about it. But once again, it feels like more work than it should be, because you have to own and maintain the queues, you have to put the messages in and take them out, and then there's the issue of, I do some work, I send it down the queue to the next worker, and suppose they blow up or get throttled or something bad happens, and I want to retry. Well, once again, you're going to have to do a bunch of extra work to engineer that and make that happen. So let's assume, hypothetically, that we wanted to build a service that would take care of all this stuff for you. Let's talk about what our must-haves would be. Now, I think all of these are non-controversial, not to say blindingly obvious, but I want to zero in on the last two. We've shown that we can do all these things using existing machinery, so I think if we're going to build a serverless coordination framework, perhaps our top goal should be that it's easy. I mean, this stuff is easy to talk about. I want to run this function and that function. I want to catch an error and retry. I want to run these three in parallel. It's easy to think about. It's easy to understand. Why shouldn't it be easy to just do? And then the last thing I want to mention there is something that we really do need to focus on more. All these various ways that people are using to coordinate and integrate multiple functions tend to have a failing when it comes to auditing and debugging, and there's no one place to go and look for the log and see exactly what happened. So I think that should be pretty important as we work through this. OK, so enough preamble. There you go. AWS State Functions announced today. It is right now generally available in 5 regions. I was just looking at the graphs before I came in here, and there's people starting to run them. So cool. And it offers multicolored boxes and arrows as a service, a new paradigm. We're going to be in the Gartner Magic Quadrant, I bet you, for that one. So it's actually a fully managed service that tracks and coordinates and manages application state and does all the things we were just talking about, and is really easy to use and has a centralized audit trail and scales down to little one-off shell script replacements or up to billions of invocations. And when I say billions, I'm not arm-waving. The predecessor product to this is actually in active use inside Amazon, both on the retail side and on the AWS side, and as we speak is currently running 1 billion state machines a week. So this is well debugged, shaken down, robust code we're talking about here. Now, for those of you who know about the existing AWS service called Simple Workflow, this service actually uses quite a bit of the Simple Workflow backend. But don't let that scare you. It's not nearly as complicated. It's really, really easy, as I hope to prove to you in the rest of this talk. So what is this thing at the end of the day? Let's go back and quote from that 12-factor app. Any data that needs to persist must be stored in a stateful backing service, typically a database. And that's all this is really, optimized for the problem of running distributed applications in the cloud. So those boxes and arrows on the screen right now are actually grabbed from the Step Functions console. And you may have noticed that only 5 minutes into this talk, we've seen a lot of boxes and arrows and nodes and arrows connecting them. And I don't know about you, but when I see those things, I think of state machines, because I'm an old geek. And so if you had a really bad time in third-year comp sci with the state machine unit, my sympathy, and you might find the rest of this talk a little tough because it's going to be state machines and more state machines. But personally, I like state machines a lot. And I've had really good experiences deploying them at various times in my career. And the notion of making it easy for anybody to use them to orchestrate serverless stuff makes me happy. Having said that, I'm totally not going to spend any time diving into the theory of state machines or the math, because this is not a computer science class. I will note, however, that a craps table is clearly a state machine, if you think about it, since we're in Vegas. And where I'm staying over at the Wynn, the room lights are a very complex state machine. Anyhow, so this is an Amazon service, and as a result, it has an API and a CLI and all that stuff, and we'll talk about that. But I thought it would be easier to start with some actual concrete use cases and examples. And let's start with the simplest imaginable use case, which is I want to run one function, and then I want to run another function. So the customer who's doing this, they're called Food Panda, and they are in the takeout meal delivery business and focusing on the developing world, and they're really making great use of cloud infrastructure. They've been in the Step Functions beta. Their problem is deceptively simple. They take orders for meals, they have deals with meal providers and trucks, and they get the meals to the hungry, which means, as a subtask, they have to solve the traveling salesman problem, which is NP complete, but they're smart. So they want to do most of this with Lambda functions. So this is the actual state machine that they wrote to solve this problem. And most of the states here are executed by Lambda tasks. But I want to zero in on one small part of the problem in the middle there, where they run their assignment code and then dispatch a vehicle, which is an obvious basic thing that many people want to do all the time, run this Lambda, then that Lambda. And I also want to zero in on just 2 states, because that way I can fit it on a slide. So here's an actual shot from the Step Functions console. And I don't really feel guilty at all about investing time in this moronically simple sequencing problem, because I think it's an important use case, and maybe at the end of the day, the single most common use case for a multifunction approach. So This is something that sounds easy, and it should be easy. So there's a visual rendition of the state machine at the top half, and a JSON expression of it on the bottom. So this is an actual screen grab from the state function. Oh, I already said that. The picture is self-explanatory. So let's look at the JSON. A state machine's top level has a structure called states, which contains, well, the states. And it has a field called start at that says where you should start. I feel like an idiot saying those things. They're so obvious. So in this particular case, you start at the run assignment algorithm step, and then you do that, and you proceed to the dispatch vehicle step. And you can see the next field in the first state that points at the second. And of course, you do this with a Lambda function. Okay? So it's easy enough. Step functions, and if you look in the second state, you can see end is true. So that's how it knows it's the end of the work of the state machine. So step functions goes through the states and executes each and moves on until it gets to the end. Obviously, it can get way fancier than this. But let's use this one to dive into how these things work. So I didn't actually include Food Panda's actual Lambda function. I got rid of those and substituted demoware. And in fact, if you look closely, it's the same function in both places. And here it is. I hope you guys can read node code. So all this function really does is tweet to prove that it ran. So ignore the first couple of lines, and let's start here. So in any state, you get input, which is a JSON blob, and it assumes that this has a field called input list, and it assumes that this value of this field is an array of strings. So it pops off the first string, and then it goes and tweets that. And assuming that it all worked, it passes on to the next state, that list that it popped the first thing off. OK, so I was going to do live demos, but I'm too chicken, so I'm going to show you a screencast I made a couple of days ago instead. So here's the state machines console with a couple of state machines on it. Pardon me, the step functions console with a couple of state machines on it. And I'm going to run that one called Food Panda. And without further ado, I'm going to execute it. And remember, it wanted there to be a field named input list. Pardon my slow typing 2 days ago. And it wanted the value of input list to be a string array. So let's pop a couple of strings in there. Yeah, I was typing badly 2 days ago. Happy Thursday in Las Vegas. But I said I typed this Tuesday. So having provided the input, let's go and run that puppy. As soon as I do that, it draws a picture. The first thing is colored blue. It means it's executing. Now, that's a bit of a lie. It's already finished by now. It's just a couple of Lambda functions. But we're waiting for the console to update. Now, the console will update in, there it is. And it shows that both of them ran and completed successfully and turned green. Now, if you look at the bottom, there's that audit trail I was telling you about. So it walks you through what happened. You know, the state machine started. It entered this state. It scheduled the Lambda. The Lambda ran. The Lambda succeeded. The task exited. The next. And of course, this is a standard AWS kind of history format. There's an API. You can fetch it. Let's go back up. Come on, Tim, 2 days ago. I'm finished talking about that. Yeah, let's go back up and look at, well, I'm going to click on that first state, and then I'm going to go over on the right there, and these are debugging aids. So I can see there was the input to the whole state machine. And if I go down, and there's the output from the whole state machine. If I move down and click on the details for the step, I can see that its input was, well, what I typed in, and its output was the same, only with the first thing piped off. So you can see how this sort of works. Now, we should actually not take it on faith. See, let's go over to Twitter and refresh it and make the you may care about thing go away. And there are the first Happy Thursday from Vegas, well, with a Google Cloud ad in between. So cute. Anyhow, let's go back here. So now, what I just did was show you running a state machine in the console, which is not a crazy thing to do. But in fact, we don't really do most of our work that way. You know, the real truth is the API behind that. So let's talk about the API a little bit. So the API, and this isn't the whole API. There's some more stuff. And I'm not going to dive into the details of methods and arguments and so on. But I'm going to give you a 50,000-foot view. So there's some more API that I'll show you later. But this is everything you need to run what I just showed you. So the first thing you do is you're going to create a state machine, which you define in JSON DSL. Let's take a quick side trip over to the console. And so here's the create state machine screen. And you can see that it's got a bunch of blueprints, just like Lambda. So there's a bunch of pre-cooked state machines that you can take and edit. Going back to the API, so probably the most important API call is the one to run a state machine. in the cloud. And that you give that a JSON blob, and it gives you an execution ID, which is a handle that you can use and use to describe the execution, get its audit trail, kill it if need be. And there's obviously the standard APIs to list your state machines and list the executions. In case it's not obvious, you can have hundreds or thousands or any number at all of executions of the same state machine live at any one time. And that's what we'd expect. Now, there'll be one-offs, a few cases where you used to write a shell script, but it's just easier to do this and orchestrate your Lambdas this way. But you know, I'm sure there's going to be people who have production ones that run hundreds of thousands wide, and I know that because we're doing that actually inside Amazon. Now, let's go back to that first step, where we create a state machine by uploading a JSON DSL. So there's the specification of the DSL. And there's its URL down there at the bottom of the screen, stateslanguage.net/spec. Oops, pardon me, that's wrong. It's actually spec.html. Pardon me, stateslanguage.net/spec.html. And it's a standard, easy to read specification with a nice friendly license at the top. Why is it in JSON? I mean, it could have been YAML or XML or ION, or we could have invented a new syntax, and I just don't want to have that argument, really. JSON, you know, is so widely implemented these days that it's kind of the thing you should use unless there's a really good reason you shouldn't use it. And it has the advantage that I can show you examples, and you can read them without, you know, ever having seen this language before, which I think is a pretty big deal. I should say, however, that I found there was a pretty close correspondence between what we needed to have in the states language and what JSON can do. Having said that, I personally hate hand-editing JSON. I can never, ever get the commas right. And so I wouldn't be surprised if there were higher order ways of specifying state machines that compile down to this. This may end up being the state machine assembler language. Now, I see that a lot of you are now looking at your laptops, having clicked on that URL, and that's fine. Go ahead and read it, see if I care. But I'm going to show some code that's not in there. So it turns out that when you upload a state machine, the step function service runs a syntax checker that throws it back at you with a 400 code if you fat-fingered it. And that's really, really annoying, particularly when you're trying to develop a state machine. So there's a Ruby gem called statelint. What a great name, that you can go and download and use on your desktop or laptop or wherever to check it. The construction of that validator is actually a little bit interesting and does not rely on JSON schema. I wrote a blog on it. My blog's easy to find if you know my name. Anyhow, let's go back to some of the things we can do with state machines to build serverless applications. So we talked about running them in sequence. The next thing I want to do is route execution to a particular state machine based on the data that I'm dealing with. Common thing to want to do. And the customer we talked did this work in this case is called The Take. They are a movie marketing company. So if you like the coat that Matt Damon's wearing in a movie, you can go to them and they'll help you buy it. And they get requests and they route them to a bunch of different retailers, only one of whom is Amazon. Oh well. And then they also have a screen scraping facility. And so in order to do what they wanted to do, they wrote this state machine. Some of those boxes are Lambda functions. It's all pretty straightforward. Now, the interesting part for what I want to talk about now is that box at the top of the screen that is labeled choice state that decides which way to branch and which Lambda function to call. So let's dive straight in and look at the JSON for that. I think it's pretty self-explanatory. This particular choice has 5 branches. Now, if you look closely at the choices field, it's an array. So it works like a case statement in a programming language. It goes through the elements of the array, until it finds one that matches, and then follows the next pointer. And the way it does it is it's got this field called variable in there, and the value of variable is a JSON path. JSON path is a widely implemented, popular thing for pulling data out of JSON blobs. And it turns out that in this case, for the choice in the first branch, it looks at the variable field. And if the value is screen scrape, you can see where it goes. I don't think this requires that much explanation. I should say that in this case, we're doing string equals, but we have a full suite of comparators. There's numeric and Boolean and timestamp. Timestamp is nice to have. And it's got greater than and less than and greater equal and all the stuff you'd expect. And it's got and or and not, so you could build hideous, deeply nested Booleans that I would have no hope of fitting on a slide here, so you're not going to see it. Sorry. So I think it's pretty obvious how this works. I want to emphasize once again this notion of passing data along from one state to the next and acting based on what that is. That represents the transient state of your whole application that's in progress. So generally speaking, each state gets some input which can update or replace and then passes it on to the next state. Let's talk about another thing you might want to do. I want to retry functions. Here's another service. Now, I'm speaking for myself. My software always works first time and never ever fails, so it never ever needs to be retried. But in the cloud, we have dependencies. And I've found that when you're trying to dodge the blame for something, dependencies are very helpful in that. And in this particular case, they have a dependency on a RESTful API that, mysteriously just sometimes fails. Hard to believe that such a thing could happen, I know, but, in the real world, it just might. Fortunately, it doesn't fail that often, so let's just dive into the JSON and see what happens. So in this particular case, they've only got one state in the state machine called callout, and it's got a retry field. And it says that if you get a handled error, which is what this particular Lambda happens to emit, keep retrying, as many as 10 times if necessary. There are some more arguments I could throw at this, and if you look closely, you can see that the retry is a variable field, square brackets there. So you can have catchers for lots of different errors with different retry policies for each. So let's actually run this rather than talk about it. So back to the states machine console, and this time, 2 days ago, I ran this other state machine called RESTful callout. Let's run it, and in this particular case, I'm not using the input, so let's just run it. And there it goes. So it's blue because it's running, and if we look at the audit trail, we can see that the Lambda function was started, but oops, it failed. Give it a minute to run, and look, it took only 2 tries. Yes, I did some other screencasts in which it failed 11 times first, but this is the one I'm showing you. So once again, I want to emphasize that audit trail at the bottom, which showed you exactly what happened, what failed, how often, thoroughly greppable. State machines are your friends. So we've talked about running state machines in sequence and branching based on data and dealing with errors. So what else? So Lambda functions are stateless functions in the cloud. And whenever I think about stateless, I think about parallel. I want to run them side by side. So here's another customer who had an interesting problem. They want to have their customers take a picture of a thing on their product and send it in to enter a survey contest. And they want to OCR, optical character recognition, on the picture the customer sends in and process that. Now, anybody who's ever dealt with OCR services knows that they can be a little bit chancy. So what they want to do is actually send it off to 3 different OCR services in parallel and get, there's a picture of what they do, and get the best one back, get them all back and pick the best one and go forward on that basis. So there are 3, and of course they don't want to do this in sequence because the customer's sitting there waiting, so they want to do all 3 of these in parallel. So there are 3 branches, each with a couple of states. Now, I don't think that's hard to understand. It turns out that the go1, go2, and go3 are the states that actually send the image off for OCR. And furthermore, it turns out they all use the same Lambda function, which knows how to send something off, get the OCR result back, and see whether it likes it or not. And so the prep states, prep1, prep2, and prep3, are just to set up each of the Lambda function states to point off to the right vendor, OCR vendor. So to make that easier to understand, let's just dive into the JSON and have a look. So what we have here is a parallel state, one of the things that Step Functions comes with. And a parallel state will have multiple branches, as you saw on the slide before. I could only fit the left side branch into the slide here. And so and each branch is a tiny little self-contained state machine with its own set of states and start pointer. And the first state in this one is called prep1, and it's not a task, it's just a pass, which is a no-op, the name being a call out to Python for the Pythonistas in the crowd. And all it really does is stick some JSON in the output. So a pass state can set up the JSON so that when the next state, the go1 state, is called, its Lambda function will get an input saying OCR provider 1. Now, the keen-eyed among you will notice that the actual function I used was the same one I used before to tweet. So if I did run this thing, you'd see 3 tweets almost exactly at the same time saying OCR provider 1, provider 2, and provider 3. So I think parallel's a really big deal in state machines and serverless applications because that's what Lambda's built to do. I would be unsurprised if we had customers running monster state machines that had thousands of parallel executions, potentially with nested states, each with hundreds of parallel executions. I think that's a perfectly natural thing to want to do. Now, I'm going to keep banging this drum because I think it's important. I'm assuming you've noticed a pattern here, which is that Step Functions is all about managing application state in the cloud. Now, a large part of your application state lives in your own databases and queues and so on. But the actual transient state that we use to track the progress of a single task or single request or single job through your distributed serverless application is captured here. It's captured in these blobs of JSON that pass from state to state. So the basic idea, and in fact, the way we do it is the same way that you guys have been doing it yourselves. We stash it in a database and persist it that way. It's just that we offer that as a service, so you don't have to. The basic idea is that a state machine execution has an input, which is a JSON blob. Now, in another life, I'm the editor of the IETF JSON RFC, so you'll allow me to be a little bit pedantic here. It turns out that the input to a state machine, to be exactly correct, is what's called a JSON text. Now, for those of you who are JSON weenies, that means that it doesn't have to be an object or an array. It can just be like a number or a string with quotes around it, or true or false or null. Those are all perfectly good JSON texts and can be and routinely should be passed along between states. Anyhow, the state machine has an input text, and that becomes the input to the first state. And the output of the first state is then passed to the second state, and so on. And eventually you get to the end, and the output of the last state becomes the output of the whole state machine. That's not complicated and hard to understand. Now, it turns out that it's a little more complex than that, because sometimes you don't want to feed the whole blob of state that's going through to your Lambda function. You just want to feed some information. Let me make that concrete by showing you an example. So suppose I have a Lambda that can add up an array of numbers. That's all it can do, OK? And I have a task state there in the middle. But the input to this state is a nice little JSON object with a title and another field, which is the array of numbers. And so what you can do is in the specification of the state, you can say input path. What that means is that it just pulls out the array of numbers, and the Lambda function, all it ever sees is the square bracket 3, 4, close square bracket, and which is what it knows how to handle. JSON path is, if you haven't seen it before, it's really simple, it's really easy. There's implementations in every programming language. Go check it out. Now, there are some corner cases here. Now, you notice in the machines I showed you so far, there weren't any input paths. And if you don't provide an input path, well, the default is it just passes the whole thing, whatever came into the state, to the JSON function. Sometimes you're going to want to run to the Lambda function. Sometimes you're going to want to run a function strictly for side effects, to update a database field or something like that. So you can arrange for it not to have any input at all. You just say input path nil, and it'll just get an empty object. And for those of you who really are expert at JSON path, you will know that you can actually have a JSON path that produces multiple outputs. And if you do that, we wrap square brackets around it and hand a single JSON array to the task. So this is just bookkeeping, but I think it hits actually a pretty useful 80-20 point. So I've talked about the stuff coming into a state. Now let's talk about the stuff going out of a state. So let's go back to that same example. Suppose that Lambda function that knows how to add arrays of numbers, it just produces a single number as output. So in this particular case, its output would just be the single character 7, which is a perfectly fine JSON text. But we don't want to throw away all our input and just have 7 be the output. So there's another field here called result path. And that says, take the input and then take the output from the Lambda function from the task and stick it into the input at that JSON path. And so you can see what the output of the state is at the bottom, right? So we've pulled the array out of the input, raw input. We've fed it to the Lambda function. We've taken the output from the Lambda function, and we've jammed it into the input state and passed that on to the next state in the state machine. Once again, Not all that sophisticated, but it hits I think a super useful 80-20 point. Having said that, I wouldn't be terribly surprised if sometimes state machines have lambdas that are only there to rearrange the JSON and get it ready for the next state. But I've actually seen this pattern. I saw one customer had a thing where they put just a very little object with just the customer ID in at the top. Then they successfully enriched it by putting in account numbers and phone numbers and email addresses and so on with just this style of computing as they passed through the state machine. Once again, there are some corner cases. If you don't provide a result path, like I hadn't in any of the state machines I've showed you so far, the output from the task just becomes the output from the state. You can also arrange to have it just thrown away, once again, if you're just in it for side effects. And you're not allowed to have plural JSON paths in this. Not acceptable. OK, that's enough about bookkeeping and data flowing through. But let's go back to some more customer situations and how they used state machines to address them. Gosh, I'm running fast. Going to be lots of time at the end. This is a simple service. Let's talk about try, catch, finally. Every programming language in the world has try, catch, finally. And you've already seen a retry when I retried that Lambda function until it worked. But you need more than that. You need to say, try doing this. If it blows up, well, go do that instead. And no matter what happens at the end of the day, do this. And of course, you could do that in your Lambda function. In this particular case, the customer who's doing this is, pardon me, I missed a slide there. Oh, I guess, yeah. OK, I missed, there's the slides being skipped over, but it's not that important. So the customer here is a customer called OutSystems, and they provide a platform as a service, and they really care a lot about reliability. And so they care a lot about try, catch, fail, and resisting errors when they happen. So this is the state machine, OutSystems, that they built to implement this one particular task they needed to accomplish. As you can see, it stretches out a bit and gets a little bit complicated. And it has a lot of error handling, because anybody who's in the platform as a service business knows, reliability is something you really have to care about a lot. So this is a serious state machine that does some heavy lifting and a lot of try, catch, finally. Now, you could say that, in JavaScript or Java or whatever, you have the programming idioms you need to do try, catch, finally. So why don't you just do your error handling right there inside your Lambda function? And, you can. There's nothing wrong with that. But I would actually prefer not to. I would like my Lambda functions to be single-purpose things that just do one thing and do it well. And if they blow up or something goes wrong, let's take care of that at another level, at a higher level, at the state machine level. So I want to show you what the try, catch, finally language looks like. But once again, I'm dealing with the size of a reInvent slide. So let's use a smaller state machine. So here's a much smaller state machine that knows how to access some media. And if it succeeds in accessing the media, it moves directly to graceful exit. And if it has a problem accessing the media, it goes to a cleanup state, which runs another cleanup Lambda function. And if that in turn breaks, there's still a second level of fallback. I think Tim ran one of these. He just talked just before me. Anyhow, let's look at the JSON that you have to write to accomplish this. OK, so this time we have a state called access media. And it runs a Lambda, just like everything else we've seen here. Only it has a new field we haven't showed you yet, which is a timeout. So this says that Lambda is only given 2 minutes to complete its work, 2 seconds to complete its work. And should that pass, it will be failed with an error code of states.timeout. OK? And if that happens, that error code would be caught by this retry clause. Now, I've already showed you one retry clause, but it was kind of dumb. It just said, keep going, give it 10 times. This retry clause here is quite a bit more sophisticated. It says not only how many times can you retry, but how long you wait and how much you increase the backoff by each time. So, if it fails, it'll wait 2 seconds and retry. And if it fails, times out again, it'll wait 3 seconds and retry. And if it times out again, it would wait 4.5 seconds only. It won't because we've only allowed 2 retries. So with 1 attempt and 2 retries, it will run a maximum number of 3 times before it gives up. And should that happen, should it time out 3 times in a row, or should the Lambda suffer some other catastrophic failure that we haven't accounted for, that would fall through to the catch clause. And once again, catch, just like retry, is an array. So you can have different catchers for lots of different error conditions, and it would branch to the cleanup state. So of all the things in step functions, I have a sneaking suspicion that this might be the single most useful. And I kind of think that you really don't want to write any serious serverless code with orchestrated multiple functions without having one of these. And I also think that it might be the case that a high proportion of just the standalone single Lambda functions in the world might benefit from having one of these things wrapped around them to deal with it when necessary. OK. Let us talk then about the last thing that I'm going to talk about in terms of how this works that we hear about from customers. And this is the situation where code that runs for hours or a long time. And the world has a lot of this stuff. Obvious examples are transcoding huge media files, or inverting mega matrices, or running legacy Fortran code, or whatever it is that floats your boat. But it happens. And whereas the amount of time that Lambdas are allowed to run is growing, there's going to be things where Lambda is just a poor match. Let me give you one concrete example. And this is the example of somebody who wants to monitor some equipment for an 8-hour shift. Now, this is just a wildly inappropriate thing to do with a Lambda. And so how are we going to do this? Let me show you the JSON oh, no, first of all, we need a new API to do that. Because so far, all I've showed you is how to call Lambdas. So we need a little bit more API for this to work. So in the state machines, there's a thing called a task. And a task can be a Lambda, or it can be one of these things called an activity. And the way it works is you register an activity, and it gets an ARN, so you can refer to it. And then you write some code that actually does the activity. For example, monitor a machine for 8 hours at a time. And then the way it works is that task that you write, the code that you write, polls the service. Good old-fashioned HTTP long poll, and says, here's the task I know how to do. You got one of those for me? And if the state machine has progressed to the point where it wants one of those tasks done, the service will hand that task to it. And then once you've done that inside your own code, when you're finished, you can report back success, or you can report back failure, or you can report a heartbeat to say, here, I'm still here, I'm working, everything's OK. Now, this code, it can be anything that can make REST calls to do this. So it could be running on EC2, it could be running in an ECS container, it could be running on your own desktop at home, it could be running in your own data center, it could be in any programming language you can possibly think of. Now, OK, yeah, I acknowledge this is not exactly serverless, but once again, I think that the serverless world and the legacy serverful world need to get along and be best friends. So we need to walk both sides of that street at certain times. So let's actually do a state machine that does that. So once again, there's a few interesting lessons in here. So here are 2 states in a state machine that actually use one of these activity thingies. The first one is a wait state, which is something that's logically necessary to have in a state machine, even though I hadn't talked about it yet. Now, a wait state can literally say wait so many seconds, or it can wait till a provided timestamp, or it can do what we do here, which I think is actually more interesting, which is to take the input JSON that's coming in and pull out a field, which is expected to have a timestamp semantic in it, saying, here's where I want you, when I want you to start. So you're going to send us a JSON message with a field called shift start that's going to say, we'll start this at 4 p.m. or midnight or whenever it is your shift starts. And the state machine will then just lock up and wait and do nothing until that time comes around. Then the step function service will wake it up and put it to work. And then it'll go through the next pointer there and go off to the gather plant data. Now, this task state looks just exactly like all the other task states that I've been showing you. In fact, to see any difference at all, you have to look really closely inside the ARN, which is no longer a Lambda ARN. It's just one of these registered activity worker ARNs. So when the state machine executes this, it'll say, oh, OK, is anybody out there polling that knows how to do this PL watch activity? If so, here, I'll hand it off to them and get it to work. And in fact, if you think carefully, there's a big extensibility point here. Essentially, we have a task state, and the thing that it's supposed to do is just a string, which is an ARN. And at the current time, we support lambdas, and we support activities. But there's no reason at all that we couldn't support, I don't know, something involving perhaps Docker containers or something like that you could conceivably identify with an ARN and launch. There's no reason at all that it couldn't just be a URL. And you go and post the thing to an HTTP endpoint and wait for it to come back. So, I think you can expect lots of other kinds of units of work to find their way into state machines going forward. What else? Oh, yeah, the timing's interesting here. So it turns out that an 8-hour shift is 28,800 seconds, and so it's got a total timeout of 30,000, and it will not let this thing run longer than 30,000 seconds. If it does, it'll fail with a timeout error. It also, notice the heartbeat thing there, too. Remember, there's a heartbeat API, so the task that's doing the work can call back to the service every so often and say, yeah, I'm still alive. Now, in this particular case, if it doesn't call every 2 minutes or more often, the service will conclude that it's locked up or frozen and declare an error, which you can probably not retry in this case. You probably just want to catch it and launch it. I'm not sure what you'd want to do. Anyhow, so that's long-running things. So I guess that raises an obvious question, which is, well, how long can a state machine run? And the answer is, in principle, forever. However, we have a limit of 1 year. We do not allow state machines to execute longer than 1 year. No, you're laughing, but people are already asking for it, OK? They're saying, the brutal truth is, the reason we have that 1 year in there is that we're pretty sure there's a good chance that any state machine that's been running for a year is probably a forgotten, pitiable orphan state machine that they lost track of and needs to be put to sleep for its own good. So at the moment, clearly the construction of this service was driven in large part by the necessity to orchestrate lambdas and things like that in the serverless cloud. But Step Functions also comes ready to run with long-running functions and stuff like that as well. OK, so then have I said everything I'm going to say? Yes, about this. So let's go back to that list of things that we think people want to do in serverless applications and ask the question, well, is this you? And I think there are actually probably quite a lot of you. This has not been a complete tour of Step Functions, but it has covered really a lot of it. There are very few parts of it that I didn't at least touch on. This is actually a pretty simple service with a pretty small API. The most complicated thing about it is the actual JSON language they use for describing states, but even that is not that complicated. The product managers who, as an engineer I nominally work for, have this vision of people running massive, complicated state machines to do business-critical functions, and having tens of thousands of them running for hours at a time. And in fact, that's how a lot of Amazon's publishing activities get done, and that's fine. But my own personal itch here is I see so many people writing these nasty little shell scripts, nasty little shell scripts to automate, deploying something or configuring something or cleaning something. Yeah, you wouldn't do that. Cleaning something up, and I just know they look like ticking time bombs to me, because, do I trust that the person who wrote the shell script, will safely keep the state between, as you move from one Lambda to the next, will they carefully track and persist and back up and replicate and do all that AWS durability stuff with the state and so on? And I think probably they won't. And my hope is that this is sufficiently easy that a lot of those dirty, nasty little shell scripts will migrate into cloud space and become much nicer, much cleaner little JSON state machine specifications and remove what I consider to be a source of significant danger among our customers. I am almost finished here. I think that there are a lot of you. There's the front page for the service. It is no preview, no nothing like that. It's generally available. It's in Oregon, Virginia, Ohio, Dublin, and Tokyo right now today. And our intent is that it be available everywhere. We regard this as well, at least everywhere their Lambda is, a foundational element for the construction of next-generation cloud-native applications. So head on over there, try it out. We think it's easy. Now you're going to ask, is it free? No, it's not free. But the price is really, really, really easy to understand. So you think of your state machine as one of those graphs that was being driven on board, and every time you click from one box to the next, that's 1/1000th of 2.5 cents. And there you go. And also, it has a free tier, 4,000 free transitions a month, which I think should be plenty to motivate you to make all those nasty little shell scripts go away and replace them with nice, clean state machines. Yeah, the pricing is nice and easy to understand. I'm about done, and we have almost 10 minutes left. I will say that there is another related session at 5:30 today over in the compute track. That one, since it's in the compute track, is a little bit less Lambda-centric and a little bit less code-heavy and more talking about the kind of business considerations you might find applicable to doing this stuff. And then, of course, we're going to have a related session for anybody who wants to talk about this. I think they want to clear the room, so I think I'm going to be rude and walk steadfastly out the door. And if you want to talk to me, let's go outside and talk outside. That's me, Tim Bray at Amazon. Anybody who does anything with this and it's really great, send me an email and tell me about it. I'm also called Tim Bray on Twitter. Evaluation, please.